All right. Thanks everyone for asking questions. At this point, I'd like to switch over so we have time for Matti to have his talk and questions. If there's some extra time at the end, we can also open up to come back to any of these issues. All right, so Matti, I see your screen. I'm assuming others do as well.
Okay, good.
Yes.
So please go ahead.
Okay, thank you. So first, thanks for Attila for a great introduction to the topic. I'll then go into more specifics on what we have done in the CMSSW. So as we have already heard yesterday today, that various kinds of accelerators are popular pretty much close to everywhere now. And just to remind, the CMS's data processing framework, CMSSW, implements the multi-threading using the Intel TBB, utilizing the tasks as the concurrent unit of work. And then we started a couple of years ago to look into what would be sort of the most straightforward way to support non-CPU work on top of that. And then we have developed generic mechanisms within the framework to interact effectively with the non-CPU resources, and also to configure CPU and non-CPU algorithms in a unified way. And I'll describe these go into more details in the following slides. Now, in addition of these generic mechanisms, we have also developed mechanisms for specific support for algorithms that offload to the same node GPUs with CUDA, and also algorithms that do machine learning inference on remote services. I'll quickly go through these as well. So as Attila already described, our approach has been this hybrid model that we want to keep the CPU threads busy to do some work while we run something else on the GPUs, and our approach has been to avoid these blocking waits so that we can keep all the TBB worker threads, which have a well-defined number of them. We want to keep exactly those threads always busy. And the way we did it is we call it an external worker concept. It's, just to reiterate, it's really a generic mechanism. It can interface with anything that's external to the framework. The basic idea is that we replace these blocking waits with a callback-style solution, such that traditionally our algorithms, they have one function that's called by the framework. We call it produce. And now we split this function into two stages. First stage is we call acquire, and the second stage we call produce. In the acquire stage, it gets called first. It's supposed to prepare read whatever it needs to read from the event, and then launch the asynchronous work. And then the work form that in the TBB thread gets finished, and the TBB thread goes to do some other work. And then after the asynchronous work has finished, we then at some point after that, we then call the produce function, and then it can finalize whatever it needs to do, basically put some output products into the event. And the trick for this callback is that the acquire function is giving a reference counted smart pointer to the task that calls the produce. Now we use the reference counting so that we prevent this produce to be called too early in case the offloaded work is very quick. And basically when the asynchronous work is finished, we decrease the reference count, and when it goes to 0, then we specifically we enqueue the task into the TBB task arena. This is an operation we can also do out from a non-TBB threads like the CUDA runtimes or drivers thread, and it's very quick operation, and then relieves this CUDA driver thread to do whatever it needs to do. And a nice property in this mechanism is that it's capable of delivering exceptions. So if there is any kind of error happens there in a work happening outside of CMSSW, we can propagate it to the inside the CMSSW and then act accordingly, which is typically aborting or doing a graceful shutdown of the job and then report the report the error. Okay, then moving on to the unified configuration. So first to tell a bit why bother. So in CMS we want to be able to run the jobs of a given workflow at any site. It doesn't mean we necessarily do it all the time, but it's an ability we want to have. And then we also want to have a single configuration for all jobs in a workflow. Now this gives us that then we can, when we gives us the ability that when we submit the jobs, we can be agnostic the kind of hardware we want to submit these jobs to. And other consideration is that we use the hash of the configuration already by the framework to segregate the data from different workflows. So this in practice means that if we would have different configurations for the CPU and a GPU workflow or jobs, they would have different hashes. We run them in a different sites, even though they are, let's say, processing the events with the same from the same primary data set. If we use different configurations, we cannot anymore really merge the output data into a single data set, which we really like to be able to do. Then we wanted to be able to keep the CPU and non-CPU algorithms separate in the configuration. It gives us the flexibility that we do not need to touch the working code if we don't want to. It mostly means that we're currently working CPU code. It may be that a different hardware may want to group the work differently, like CPU of the current CPU workflow or job using several modules for to do something, while for the GPU, we want to combine all of those into one or just two modules. Now, while we want to be able to do that, it doesn't mean that we could do it in a simpler way, where we just have very same structure for the CPU and a non-CPU algorithms. And then we are using our provenance tracking to store the choice of the technology along the event so that we can always, after the fact, check which algorithm was actually run. And we basically exploit the framework's ability to already track.
Hello?
Matti, I think I've lost your...
Yeah, we lost you.
Yeah.
All right. Okay.
How about now?
Yes, we can hear you now.
Yeah, sorry about that. Okay. Yeah. Okay, so our framework already tracks the input data of each algorithm event by event, so we just use that mechanism. And now then, when you craft such a thing, then you also have to think about the validation. In principle, we would want to validate all the technology permutations. I believe we are going to hear about that more tomorrow. So the mechanism itself, okay, we call it a switch producer, which we added into configuration. It basically allows specifying multiple producers that are associated with the same data label, which is labeled hits in this example, which in this example, it has a CPU side and a GPU side, and then at runtime, we pick which one we run based on the available technologies on the node. And then we use the framework's ability or the feature that our consumers dictate which producers get run, such that if the switch decides that it runs on the CPU version, then it runs also this producer called clusters, which is a dependency of the hit producer. But if it decides that we run on a GPU, then we skip running the clusters because the GPU module they took its input directly from the raw data. Okay, then moving on to the specific support for CUDA. First, some design considerations. So our especially reconstruction code has a relatively flat time profile. Okay, there are some functions that take more time than others, but typically speeding up single functions has a small impact at best. And our code also tends to process quote large amount of data with relatively low arithmetic intensity. Now large here means that it's larger than typical cache sizes, especially if you consider the temporary data structures, but it's also small in the sense that it's not enough to fully utilize the GPU with the data of one event. And if we would just go to offload these highest cost functions, which are spread somewhat randomly, it could easily get limited by the transfers, especially if we would have to transfer large temporary data structures. Basically, this means that to maximize the event processing throughput, we would need to run kernels concurrently and overlap them with data transfers as much as we can. We should offload long chains or even graphs of algorithms, even if some of these algorithms would be a poor fit for the GPU by themselves. But if we can avoid transferring hundreds of megabytes per event, with that it can well be worth it. And then we really need to minimize the data transfers between CPU and a GPU. And going a bit into more details what we did for that. So to allow the CPU to do the other work while the GPU is running an algorithm, we are using only the asynchronous API and the CUDA streams, which are the concurrent work queues in CUDA. We use the CUDA callbacks to notify when the CPU can proceed, and we typically do this only after we issue a transfer from the GPU to CPU memory, because otherwise the CPU doesn't really have to care what's going on the GPU land or on the GPU side. We had to add a mechanism for a chain or a DAG of algorithms to share a resource, for example, a GPU memory. For that, we introduced a wrapper for event products that holds the CUDA device ID and the CUDA stream. And we try to reuse the same CUDA stream for subsequent work whenever that's possible. To transfer the data between GPU and a CPU only when necessary, we use the framework's ability to run the producers only if some other module consumes it. It means that if no one asks some data product on the CPU, we don't transfer it. We believe this is extendable to multiple device type, and it certainly supports multiple devices per device type. Our experience from this model is that it seems to work pretty well. There's a link to a JEP talk with more performance numbers. Some limiting factors we've experienced include that the CUDA API itself is thread safe, but it's protected with a single mutex, which then means that if we have many small concurrent CUDA operations, this mutex can become contended. Then each CUDA operation has about constant overhead. Again, if we have many small CUDA operations, the relative cost of this overhead becomes something that you can actually see. And when talking to especially HPC experts, an often proposed solution for these many small operations is to start to batch event data, which is somewhat non-trivial, but we have started to explore at least the scheduling strategies, how such an event batching would look like from the scheduling point of view. Then one performance comparison about to motivate to show that the external worker is actually beneficial. This is comparing an event processing throughput of a simulation of the Patatok pixel tracking application for the variant which we transferred the structure of array results back to the CPU. This basically measuring the transfer sizes, kernel times, and CPU times from the actual application, and then repeating with toy operations. And this is showing the throughput of one job as a function of the concurrent events, such that the node is filled with up to the 64 hardware threads with the CPU consuming work. And you can see that there is, depending on how many concurrent events you have the external worker is showing benefits. Okay, moving on then to the remote services quickly. So here the idea is that you convert the experimental data to a neural network input and send that to a separate coprocessor being somewhere using a communication protocol. It uses the same external worker mechanism for these asynchronous non-blocking requests, currently supports gRPC with TensorFlow. It was tested with Microsoft Brainwave, which uses FPGAs, but it's compatible with any service that uses gRPC and TensorFlow. And recently a support for NVIDIA Triton was added for GPUs, which can also serve models, other models than TensorFlow. And to conclude, so we have added these generic building blocks to continue the exploration of the non-CPU resources. We have some specific support for CUDA and machine learning inference. We really need more experience with those to go on. And just a quick note about the portability that was discussed more yesterday. So we are looking into technologies like Cocos, Alpaca, and Sickle. We are really aiming for this single source, or dreaming about the single source approach for GPU capable algorithms. We now have to understand how our CUDA support model could be evolved for those technologies. We actually have two timescales here. First one is for run 3, where we want to achieve the portability between CPU and CUDA to support our HLT developments. And then for run 3, we are aiming to be, quote, as portable as we can. Thank you.
Thank you, Matti. So if you could stop sharing your screen, and we'll switch over to Kyle if there's any questions on the live notes.
Okay, yes, thank you, Matti. A couple questions. One from Paolo. How will CMSSW or others handle offloading of non-event data, for example, alignment, including when a GPU is processing data from multiple events?
That's a good question. So it's turned out to be surprisingly simple. I mean, the model that we currently have for conditions data is that, okay, you have to first craft a data structure that you can actually ship to the GPU, which then basically means plain arrays. And then you transfer it to your GPU or all of your GPUs if you have multiple and want to support them, and then you hand off the pointer or pointers to the GPU memory to the algorithms that then make use of those. But at least in CMSSW, it actually fits into our model for calibration data and their intervals of validity pretty naturally.
If I can, I think the reason Paulo asked this is that in CMSSW, you have some explicit synchronization points for alignment changes and these sort of changes, right?
Yes, although I mean, we are transferring those, I mean, for CUDA, we are doing the transfers asynchronously. Then the trick is that you then have to, where in the module or in algorithm which makes use of them, we use the CUDA stream wait event to synchronize the CUDA stream of the computations that use the alignment to the CUDA stream which transfers the data. So we can still queue work that use the alignments while the transfers are still going on, but we are not, and we then let the GPU or CUDA or the GPU to deal with that synchronization, but the CPU side can proceed.
Oh, okay, thanks. I actually didn't know this. I thought that maybe the CPU would have to wait for the new calibration to be uploaded at this point. Like all CPU threads would have to wait, but if not, yeah, that's great.
Okay, and then we have another question. Well, I had a question. So in the example of using the switch producer that you showed on page 6, there was a DAG that showed if you were using the CPU, you had these 2 boxes, whereas if you were using the GPU, you just had this one box. Does that imply there's some merging of metadata that has to happen in that case?
Yes and no. Yes, in the sense that yes, you have all the metadata available, but no, in the sense that we are not doing any explicit merge there. I mean, the provenance metadata is actually split in two. There's one part which is common for everything, which is then sort of shows you all the possible ways how things could go. And then we store event by event what actually happened, which is in a more compact form. So in that sense, we don't have to explicitly merge anything beyond what we are doing already. But we can event by event inspect how exactly that event was processed.
Okay, so there is not a requirement that event by event you must have a consistent history.
Correct.
Okay,
Okay.
I do not see other, I'm sorry, were there more comments? In that case, I will stop sharing and hand it back to Chris.
All right, so if there are any other further questions, people can raise their hands. Okay, we have one. Liz, go ahead.
Okay, I was interested to hear that you are having locking problems with the CUDA interface. So I was wondering, is it for the people who talk to people who work at computing centers, you know, supercomputing centers that are actually developers with CUDA, is there hope that in the future their APIs might develop a lock-free design?
I wouldn't hold my breath. I mean, if I show the profile of like the pixel tracking to like these GPU experts, their first response is our kernels are way too short.
I see.
Which is sort, I mean, it's like over half of the kernels have a runtime of the order of less than 10 microseconds, which is sort of the ballpark of just the kernel launch overhead.
Mm-hmm.
So their first response is that, okay, you should batch data.
Okay.
And I mean, we are in the regime where we are get affected by this lock contention. We are doing we are locking this pure mutex at a rate of over 100 kilohertz.
Oh, wow.
So it's, yeah.
At the same time, I would argue that there is some part on which we should be engaging the developer community. And I think that's memory management. Because so far, every single experiment that is doing something serious with GPUs ended up writing their own memory managers or memory allocators for C++, just to make sure that allocating and deallocating memory on the GPUs could be done at runtime in a more efficient way than what the basic memory management of CUDA and well, basically what CUDA allows. And I think the problem here is very similar to what Google had to solve with tcmalloc, that in order to provide good allocation and deallocation from multiple users, from multiple threads, multiple processes, some better allocator algorithms have to be developed, which may be less efficient in terms of memory sizes, because as tcmalloc is less efficient in that, but could be faster. So this could actually be some pretty good area to interact.
So we have one more hand. So let's just go to one more question and then we'll switch over to the next session. Andrea, do you want to say something?
I wanted to comment on what Attila just mentioned. Actually, the latest version of CUDA does introduce a new low-level feature for managing memory more efficiently. The one thing everybody runs into when doing memory allocations from the host on the GPU is that these operations are slow because especially freeing is blocking for the whole device. And apparently NVIDIA didn't remove this because people started counting on it for synchronization. So the new API they're introducing seems to be able to work around this. So far, it's pretty low level. As usual, maybe they will have a higher level version in the new release, or we can expect somebody to write a more efficient allocator that uses that directly.
Thanks, I didn't know that. Okay.
Okay, so in the interest of time, I would suggest that if there's any other further questions, people could put them in the live notes or talk to the speakers directly, and then we'll switch over to the next half of the session. Thanks you for everybody.